Hello, my name's Keith and this is lesson 2 of my multi-platform Z80 tutorials. So we're going to be having a look at another little program today and we're going to learn some new commands and hopefully we'll find some interesting stuff. So as I say, this is lesson 2, but don't worry if you've missed lesson 1 because we're going to be discussing this very simply. We're very early on yet, so don't worry about that. That said, please go back and have a look at the first lesson. There's good stuff in there. It'll show you how to set up Win8 for your assembly. And also, please check out my website. Each of these video lessons has an associated text-based lesson with the same kind of content on the website, and that will be uploaded at the same time as the video. Also on my website, I have a PDF, which if you're going to do Z80 assembly programming, you'll probably want to get. It's a cheat sheet, and there's two sides to it. The first side is a complete command list with every Z80 command. I'll just zoom in a bit there so you can see it. It has every Z80 command. It has the bytes which is great if you're doing some self-modifying code, and it also shows all of the flags that are changed, because often I get confused which ones do what, so that's all in there as well. It's something I definitely recommend. The cheat sheet is basically what I made myself so that I could program assembly, so I'm pretty sure it should help you as well if you're trying to do the same. So yeah, please go to my website. Please see video 1 as well. But now let's get started with today's lessons. So I'll just move these out of the way and we'll get on to my Win8 here. So we're going to create a new program. So we'll just show the assembler and we'll go into this blank file here and we'll just get started. So the first line is going to be org and 8000, and this starts the program at 8000 in memory. All of these are hexadecimal addresses, I should point out. And then the next command is going to be LDHL and 0000. So we're loading the 16-bit register pair HL with zeros. We'll explain why in a moment, just bear with me. So we do LD, DE, and C0000. And this C000 is the screen memory on the Amstrad CPC. So we're going to be doing something with the screen just so you've got something you can actually see. So we'll have some fun with that. And then the next command I'm going to type is LD, BD, and 4000. Now if you're sharp, you'll have noticed I've done something wrong here, and I've done it on purpose because I want to show you how to debug assembly errors. So we'll have a look at that, so just bear with me on this one, trust me. And then we're going to do LDIR, which stands for load increment repeat. We're going to go into it, don't worry about it, we'll have a look at that. And then the last command is ret, which is return. Returns back to basic in this case. So let's compile that and let's see what happens. Go to assemble. Get this in frame, and oh dear, we've got an error. Well, I told you I'd made one on purpose, so let's have a look at it. And you can see here, undefined symbol. Just get that better in frame. So if I just double click on this, it jumps straight here, and the reason is there's no register pair BD. There's DE and there's BC, but BD doesn't exist. So I played a little trick on you there, sorry about that. So the correct command is BC. Now let's get back to that LDIR command. What LDIR does is it sequentially copies from one address to another, and this is where our other commands come in. So HL is the source, and I believe that stands for high-low because it's a high-low address pair, or at least that's how I think of it anyway. So we're going to copy from 0000 in memory, and then the next command is DE, which stands for destination, and we're copying to C000, which, as I've said already, is the screen on the Amstrad CPC. This won't work if you're trying to run it on an MSX or a Spectrum. On a Spectrum, the memory locations are different. I'll just tell you what they would be, the equivalent ones. C would be and 4000, and BC on the Spectrum would be and, oh, sorry, have to excuse me, 1800 would work, I believe, on the ZX Spectrum. Now on the MSX, if you're going to try this, you can't do the same thing. The screen isn't part of the basic memory on the MSX. You can run the command. If you run the command as the Amstrad one does, you will crash the MSX. So the best I can suggest you would do would be to set this to leave this as C000 and just set this as 1000. And that will copy a chunk, that will do it to a chunk of memory that you can look at with your debugger. You can't see the result on screen. As I've said before, I really recommend doing these on the Amstrad, but I know some people are trying them on other systems, so I just wanted to throw that out there. But basically, if you're trying this on other systems, you are kind of on your own. Sorry, I can only I can only really explain one system. So let's just get rid of that. So anyway, the LDIR command is going to copy the number BC amount of bytes from HL to DE, and this 4000 here is 16 kilobytes, which is the size of the Amstrad CPC screen. Now let's have a look at this, and let's just let's just fire it up. So we'll do our assemble again, and now you'll see we've got no errors, which is good. And then if we do here, call and 8000, and now that might look a bit odd. We're kind of wondering probably what's happened there. We've got a kind of line of corruption at the top of the screen and then a big blank space. Now what's happening, you think? Well, I'll explain. 000 is the start of the memory, and there's a small amount of data there for the firmware, things like the interrupt handler and things. So what we've actually done is we've copied that memory onto screen. Practical purpose, really nothing, but I thought it made an interesting visual representation of what was happening with regards to the memory copy. Now, something that's quite fun with this is what we can do is we can write a little program. If we do 10 print I am a program. Now we're not going to run that because we don't really care, but if we now do call and 8000 again, you'll see another bit of corruption has appeared here. And the reason for that is that corruption, so to speak, is actually our program in memory. So when we do things that affect that low end of memory, we can now see them visually represented as bytes on screen. And personally, I thought that was quite interesting. But anyway, so there we go. As I said before, the LDIR command copies a memory range from the HL source to the DE destination, and the number of bytes it copies is in BC here. So that's how the command works. So that's a nice simple example there, and we're going to make some changes to this program and we'll have a look at something a bit more interesting. So what are we going to do next? Well, first thing I'm going to do is I'm going to change the start to 8100. You don't need to do this, but the reason I'm doing it is you can download all of these programs complete with source code comments from my website. I've compiled the entire lesson into a single file just for simplicity, so I'm changing the memory location with each example so that all the examples are in one file at the end, but you can run them the same as I'm talking them through here. So okay, let's have a look what we're going to do this time. So this time the source is going to be the screen and the destination is going to be the screen plus 1. Now we're going to do something a bit different as well. Just for an example, we're going to create a what's sometimes referred to as a symbol, or I would probably refer to it as a constant. Now what this is having numbers in our code can be a bit confusing. It can make things a bit hard, and also if you're referring to the same number over and over again, what if you want to change it? You know, you don't want to change every position you've mentioned the screen size if you change it. So what you can do is you can define it once, you can define the number as a name and then use that name everywhere else. If you change it later, you only change it in one place. So let's give you an example of that. So if we do screen size equal, EQU is of course equals, and then we're going to do 4000. And then what we can do, I'm just going to use the clipboard to save my typing. We'll just copy that and we'll put it here. And actually what we're going to do is we're going to do a little bit of maths as well. We don't just need to use, because screen size is now 4000, but we don't need to use it just as that. So what we can do is we can put -1. And when we do our assemble, if we have a look at the code, you can see screen size -1 has actually been converted to 3FFF. And if we just get our hexadecimal calculator here and we do 4000 -1, you'll see it is indeed 3FFFF. Now, so you can see you can actually get, and it's the assembler doing this, not the Z80. So the assembler's doing the work and the Z80 just gets the result. But there is a bit of a catch with regards to the way that WinApe's assembler works. It's quite mathematically crude. Now, if you're, I'm not going to do a coded example for this, but I do need to explain this. If you're familiar with algebra and things, you'll probably know that usually if you've got 5 plus 3 times 2, what you would do is you would do the 3 times 2 and then you would add the 5, because the multiplication command has priority over the addition command. And also with brackets, you would usually know that you do the thing in brackets first. Now, WinApe's assembler is very, very basic. It does it left to right, and it can't do brackets. So rather than doing 3 times 2 first, what it would actually do is 5 plus 3, and then multiply it by 2. So pluses and minuses, no problem. But when you're doing multiplication, when you're doing complex formulas, you kind of need to sort of multiply out the brackets and things. You need to work it down into a left-right format as if you were typing it onto a simple calculator. And then WinApe will do it great. WinApe can do whatever you need. You just need to sort of really get it down to basics for WinApe's mathematics. So that's just something to explain when I'm doing these symbol definitions. Okay, and then we've got one more command here. And we've got LDHL, 0. I'm going to run this and then we'll have a look at what actually happened. So we'll go assemble here, and it's no errors. And then we're going to do call and 8100. And you'll see the entire screen cleared. So let's have a look at what we actually did there. So the first command sets the source location to C000. The destination is set just 1 byte afterwards, and the byte count is set to essentially the entire size of the screen less 1 byte. Now the next command loads that first byte with a 0. Okay, and then the final command copies the source range to the destination. And I'll just give you a little example of what happened here. I'm going to change this to 255, and then I'm going to put a breakpoint on LDIR, and I'm going to assemble it. And what we're going to do is we're going to watch it in memory and see what happens, because it's quite clever. So you can see here my debugger, and we don't really care about what code it's running because it's going to be running this LDIR for quite a while. But what we do want to see is if we scroll down here to C000, so here's C00, and you can see here the first FF has already been loaded, which is of course 255. So that was the result of that command, and now our LDIR is going to run. And if you think about it, the source destination is C000, and the destination is this byte here. So let's press F7 and let's see what happens when the first iteration of that LDIR command runs. Did you see what happened? The next byte is also filled with FF, sorry. Now, just as I just said, that's because it's copied this byte to here. But if you think about it, the next command it's going to do is going to be to copy from HL, which is now this byte, to DA, which is now this byte. So we'll just press F7 again, and again, and again, and again. And what we've done is we've overlaid the source and the destination, so it's always copying its own previous destination, effectively filling the entire range with any byte we want. Now this is a nice, quick, easy way of filling or wiping a data range with a command that's kind of really designed to do a copy, but it works absolutely perfectly. The only sort of limitation, so to speak, with it is there's actually a much faster way of doing it, but it's a little bit tricky, so we're not going to cover it now. But generally speaking, if you want to wipe a chunk of memory or set a chunk of memory, whether it's the screen or data areas, this is a nice easy way of doing it, and I use it all the time, so definitely remember it. So there we go. We'll just close this down now, and if we just remove that breakpoint so we don't keep getting the LDIR pop back up, and we'll see we've filled the entire screen red, which is interesting. So okay, we've got an even more tricky example coming up next, so let's have a look at that. So we're going to leave our screen size definition up here, and as I said, if you are using the Spectrum version, you could just change this to 1800. You could also create other definitions for screen start and things here if you wanted, but as I say, this is really just an example, and I only put that single definition in there just to show you what they look like and how to use them. You'd quite possibly want to put all of these numbers as definitions. You quite possibly want to put none of them. So either way is absolutely fine. It's whatever you want in this case. In a more complex case, it would start to become essential. But in a simple example like this, it's not really necessary. But it's nice to see them in use. So okay, so this time we're going to do this as 8200, and then we're going to do LD A comma, and to excuse my bad typing because I'm on a Japanese keyboard here and the keys are all in the wrong places. So we're going to load A with this binary value where the rightmost 4 digits are 1s and the leftmost 4 are 0. The percentage means binary, just in case you're not familiar with that. And A is the accumulator. Now LDIR does not use the accumulator, so it's not going to be harmed or altered in any way by that LDIR command, and that's important when you look at what this command is going to do. So here we're going to change this 255 to A. So as I said before, we're tricking the LDIR command to do a fill, and we're going to fill with the value that's in A. And then what we're going to do next after the LDIR, we can take rid of that breakpoint because we really don't want to see all of this. So what we're going to do is going to do a dec of A, which is decrement. It reduces A by 1. And what we're going to do then is we're going to do CP 255. Not 266, that will not work. So we're doing this. Now we've decreased A, and then we're going to say to the Z80, well, okay, how does A compare to 255? And then our next command is going to say, well, depending on how it compared, do this. So what we're going to say is JP NZ, comma, fill again. And of course I've missed something here. I meant to put a label in. Fill again. Okay, we're going to have a look at this label next, and then we've got the return command. That's all correct. So a label is, it's a bit like our sort of symbol definition above, only a label points to a position in code. Now I'll explain that, as I said before, that these things are all invisible by the time the Z80 looks at them. The assembler looks at all of these kind of labels and definitions and things, and it goes, okay, well, the Z80 just wants numbers. So that fill again, where is it in memory? What memory location is it that I need to put in the equivalent places in the code when it appears later? Now, it's fairly easy mathematics for us. The org is 8200. This is a 2-byte command. So this is going to be 8202. And so this command, when it's converted to bytes, the fill again bit is going to be converted to 8202. Now let's confirm that to you. And here we go, we're assembling it. And here's fill again, 8202. My maths is doing well today for a change. And here, C2, I can't remember it, but obviously C2 is going to be the jump NZ command. We could actually confirm that, just a moment. Just bear with me a second, sorry. Sorry, I just should have done that on screen. So we've got jump NZ address, and that is indeed C2. And so that's why we've got our C2 here. And this is why these are really useful if you're doing tricky things or double checking things. Now, you're probably thinking, well, hang on a minute, you said it was going to be 8202. That's showing 0282. And that's because of a rather odd thing in the Z80 machine language, where 16-bit values are put in reverse. So when you've got a high-low pair, the low part is put first in memory and then the high part. It's a bit odd. So our assembler has worked out, well, fill again equals 8202. So when the user has specified fill again here, I need to put that memory location back in. And then all of that is irrelevant to the old Z80. All the Z80 cares is, I want my bytes, I want to know my memory locations. So all of these labels, which are there for the human to read it easily, are gone by the time the assembler gets to them. So let's run this and see what happens. 8200. Ooh, that's a strange pattern, isn't it? So I'll explain what happened there, and we'll have a look at the code. So we filled A with this value here, and then we decreased it by 1 over and over again until, now we compared to 255, and the reason for that is that when a value goes to 0 and we decrease it once more, it rolls over all the way back to the maximum value that register can hold. An 8-bit register, the limit's 255, so it goes from 0, rolls all the way back to 255, and the reason we're comparing to 255 is we wanted it to run 0. If it didn't run 0, we'll have a look at what, if we compare to 0, then it will basically stop at 1. And if we call it now, call 8200, we get a fun bunch of weird lines because we never did that zero value byte. that would be basically the blue background. So that's why I'd set that to 255. So we're comparing to 255, and then we've got this jump command and this weird N0 thing here, this NZ. And now what's that mean? Well, I should explain. The Z80 has a set of flags, and these flags, there's a few. The main ones you're going to see are Z for 0, NZ for non-zero, C for carry, and NC for non-carry. Now, carry, I'll explain carry in much more detail later, but it's basically when you add two numbers together, like two 8-bit numbers, and they go over 255, and so the single byte, as I said, can't store it all. There will be if it goes over 255, there will be a carry bit, and this is so that you can sort of extend out into a 16-bit register if you want. Carry is also used for shifting, where you're pushing bits off the left-hand side of a byte or pushing them off the right-hand side. They go into the carry again, so you can maybe push them into another register, or you even use them to roll around the register. So it's a kind of it's sort of an overflow of, well, the last command you did was in some way push data out of the byte. Here's the data that got pushed out. But rather obscurely, when we use the CP command, the compare command, these flags are actually used, and they have slightly confusing meanings, unfortunately. Now, as I say, if you have a look at my this is an ideal time to point to my cheat sheet, so let me just get that in frame. I'd suggest, if you want to use this cheat sheet, I'd suggest you print it out on two sides of A4, because I use it all the time. So you'll see at the bottom on the sort of second side, you've got here the flags and how they compare to sort of basic or possibly C comparisons, because this CP command is a bit like your if command. This is kind of saying if A is more or less than 255, then go to fill again. Now, it's not quite as nicely said as that, but that's the meaning it's got. And the point to remember at this stage is, while doing these kind of things is quite frustrating in assembly sometimes, quite confusing. Basic does compile to assembly, and so does C++. Anything you can do in those languages, you can do in assembly. And once you get used to it, firstly, you'll be able to do it just as easily. And secondly, you'll be able to do it a heck of a lot faster, because assembly is as fast as it gets once you're using it right. So anyway, let's get back to these flags. Now, as I sort of said on the cheat sheet, a Z in this case, when you're comparing two numbers, will be equals. So I'll just type these in. These are rem statements, of course, they're not real code. NZ would be more or less than or not equals in C. C would be less than, and NC would be greater than equals. And I kind of use a bit of a trick to remember these, because I struggled like crazy. I must have literally looked at that cheat sheet about 1,000 times, because every time I needed to do less than or greater than, couldn't remember them, struggled every time. But here's the sort of trick I use to remember which of these commands to use for an equivalent basic command. So if you think of the compare command as saying, well, what is the difference between these two numbers? Well, if A is the same as the number you just compared to, then the difference is 0. So that's why the 0 command could be thought of as being equals. If the numbers aren't the same, then it will be non-zero. Now, going a bit more sort of obscure here, and this is totally made up, but bear with me. If my computer game's called Chibi Akumas, which means little monsters or something to that effect. The word chibi kind of means little. So I always think of C as being chibi, and if A is more chibi, more small than 255, then the C flag will be set. If it's not smaller, which means greater than or equals, then I think of it as non-chibi, and that's how I remember them. But please come up with your own way, or just keep looking at the cheat sheet like I literally did for 6 months. It drove me up the wall every time I had to code an if statement. I had to double check in case I got it wrong. So yeah, a real pain those are. But as I say, you can do any command in BASIC in assembly, and the other thing you're probably thinking is, well, what about an else statement? Well, an else statement, you would just put another jump afterwards, because if it didn't jump here, then the other jump would definitely happen. So if I put jump give up, and then put a give up label here, that would be my my else statement. And a little more tricky, but you could even do a you could do another compare here or something, and that would be, if you did a compare and then a jump Z, that would be a bit like, that would be, if that would be the equivalent of if A equals 4, then go to give up. And you can keep doing loads and loads of these one after another, which is a bit like your case statement if that's a command you were thinking, well, where is it? But as I say, I'm comparing these to an if statement in BASIC, and that's of course true, but the effect is also the same as a for I equals 1, 2 loop. I mean, what we've effectively done here we've sort of said for A equals, well, to 0 step minus 1. I think that's right, because as I say, it would run the example here we're comparing to 255, but that's because we want 255 to run. But I believe in BASIC that would actually run 0 in that case, and we're going backwards because we're using that dec command. So as I say, assembly's got very, very few commands, but the few you've got, you can do absolutely everything with. It's just a case of learning how to use those simple commands. Now, there are a few other kinds of jump, which I will just very briefly mention, but I'm not going to go into detail. Please check the text file because they're quite complex. But there's a JR command, which is a more limited jump. It takes a little bit less memory, but it can be slower in cases. It saves basically 1 byte, which is sometimes quite important when you're dealing with 64K systems. But it does have some limitations, and it can be slow as well. But JR is worth knowing. Apart from that, it's exactly the same as JP. There's also DJNZ, which only decreases the B counter. It's designed to work with just B. It just decreases it, so it's designed as a sort of simple loop counter. I didn't use it in this case just because because I was using BC for the LDIR, but I also wanted to just show you the fully expanded loop counter with the DEC, the CP, and the JP. But DJNZ would be effectively do DEC B, CP0, and then JRNZ fill again. That's effectively what it would do. But it kind of does it all in one command, so it can be quite handy to have that. But you do have to have your B register available, and you do have to be doing less than 256. So there's that limitation as well. There's another quite interesting command, which is JPHL, and there's another few ones there, and they actually jump to the memory location in HL. Bit obscure, but definitely worth knowing, because there may be times you want to do something a bit trickier and you can't work out how to do it, and that's going to be how you do it there. So okay, I think we've covered pretty much everything I wanted to today. So all I'm going to finish off with is I'm just going to get this back to the way it was. I'm not going to show you what it does, but I'm going to suggest a few things you may want to try for yourself. Why not try changing this so that instead of all being ones over here, what would happen if you did that? Or what would happen if you did that? Or maybe you want to try changing the screen size on the CPC still, so try changing the screen size to a lower amount and see what happens then. I'm not going to show you. One thing I will say is don't change it above 4000, because that's the if you go bigger than that, you'll end up overwriting the firmware and crashing the emulator. So feel free if you want, but you might be surprised as to what's happened there. But yep, feel free to try it out. I do have another video explaining how the Amstrad CPC screen memory works a bit. And if you really want to start playing around, have a look there. Now, for those who aren't familiar with the Amstrad CPC, I will just show you something here. The screen mode we're in here is mode 1, and you can reset it by just typing mode 1. And if we type pen 1, that changes to our first color, which as you can see is yellow. If I type pen 2, you can see it's blue, which if you remember is the color we just filled in. And pen 3 is red. Now there is a pen 0, which is of course the background, which is why you can't see the cursor now. So those are the 4 colors that this screen mode can show, and that's just something to give you a clue as to when you're sort of looking at how changing this A value affects what appears on the screen. You probably need to know that to be able to sort of get it in your head exactly what's going on with that screen memory. But I definitely suggest playing with that kind of thing if you are seriously considering doing Amstrad development. Firstly, it's quite nice to see what you've just coded appear on the screen in front of you, and secondly, playing around with these little simple programs that put data to the screen lets you start to work out just how the screen's actually working in the background, and starts to give you a feel of, well, I know now I can make the screen do what I want, and it gives you a bit of confidence as well for, well, you know, now that I know how to get data on the screen, I can start to copy data. Now I can start writing my sprite routines and things like that. So, you know, definitely have a go playing with those kind of things if you get the chance. Okay, well, I think we're pretty much done here. As I say, by the time you're watching this video, please go to the website because lesson 2 will be uploaded. I strongly suggest you type in the code, but if you really can't be bothered, or if you type it in and can't get it working, I will have uploaded my samples and all of the code will be commented. I'll just show you what that looks like here. So I've written these fully commented versions. I don't put it all on screen because it would take forever and it would get confusing, but the versions uploaded have detailed comments and the actual documentation as well. In the same way as I have now, they break the entire program down line by line, explaining what each command does, trying to explain all of the intricacies of the commands. Anything else I think it's really good that you know it at this stage, because I needed to know it, or I wish someone had told me it earlier on and saved me a lot of time. I'm always trying to make these tutorials as simple as possible. I'm trying to make them that anyone can use them, even if you've never programmed before, never used an Amstrad before. I'm trying to teach you all of the stuff that I know, all of the stuff that I learned, and I'm trying to teach it in the easiest way to understand to get to that advanced level. So I'm not trying to make this a dumb beginner's idiot's guide. I'm trying to make this an advanced guide that you will learn in a very easy way, and hopefully you think I'm doing a good job. So I'll try and get lesson 3 uploaded next week if I can. Thanks for watching. Please stop by the website at least to get that cheat sheet. Thanks a lot. Goodbye.